All right, so now we are going to talk about wallets. So let's start with the definition, because currently, people define it in a wrong way. Because let's first talk about physical wallets. A physical wallet has three main purposes, right? You store your cash there, and whenever you want to pay something, you remove cash from it, and if somebody gives you exchange or something, you put it inside your wallet, so you receive cash. Many books, blogs, web pages claim that digital wallets are digital analog of physical wallets and are used to store cryptocurrency, send cryptocurrency, and receive cryptocurrency. So this analog is actually not correct, because once you say it like this, when you claim that it stores cryptocurrency or any digital asset like NFTs and so on, people think that it is stored in that software. So people think that when they install a wallet to their laptop or their mobile phone, they think that their cryptocurrencies are inside that device. But actually, all of the data are stored on the blockchain, right? It is not on your laptop or your mobile phone. This is important because some forensics people think that it is like this, so they do not connect the device to the internet, so that they think that nobody can spend it because you're not connecting the device to the internet. But actually, as we mentioned before, a transaction actually changes the ownership of a digital asset, and all you need is a private key to sign that transaction. So if somebody has that private key on another device, they can make the transaction. So this analog is not that correct. So digital wallets do not store cryptocurrency. Your wallets actually store your private keys and corresponding public keys and so on. So with some blockchain networks, users must manage and securely store their own private keys. They often use software to securely store them. This software is often referred to as a wallet. The wallet can store private public keys and associated addresses. You can actually, with this software, you can, from a single private key, maybe you can create more than one public keys or addresses and so on. It may also perform other functions, such as calculating the total number of digital assets a user may have. Your wallet checks if you received a payment by looking at the blockchain and analyzing all of the addresses you have the private key for and provide the total balance. This is how your wallet knows your total balance. Actually, your total balance distributed most probably in different blocks. If a user loses a private key, then any digital asset associated with that key is lost, because it is computationally infeasible to regenerate the same private key. So one way of handling private keys as follows. If you randomly generate it, you keep it in a file in your hard drive. But this is risky because if a Trojan affects your computer, they can steal this information. So you need to keep it in an encrypted way. So for this reason, you have to encrypt it. In order to do it, you also need an encryption key. So this is why most of the time you are asked for a password. So with that password, actually your password is hashed thousands of times with SHA-256 to obtain an output value, which is used as an AES key to encrypt this file. So if you forget that password, then you cannot recover this file, right? It is encrypted. But since it is encrypted, whenever you need to perform a transaction or anything, you have to type in your password. That is the idea. Of course, since you have to keep a copy of this file, if your hard drive is lost, even if you remember the password, you cannot decrypt it back because you don't have the file itself. For this reason, people come up with different ways to generate private keys, where you choose mnemonic words which are used to create an integer which is used as a private key. So even if you lose your hard drive or anything, if you remember those words in that order, you can rewrite them and reproduce the private key you choose initially. This is also important because if there is a backdoor in this process, then somebody else also can steal your key, right? So you have to check how these keys are generated in your software. So another misconception is people always regard Bitcoins as if they're all the same, because when they talk about NFTs, they say things like this: while all Bitcoins are equal, each NFT may represent a different underlying asset and thus may have a different value. So when you're talking about tokens, this sentence might be correct. But when you're talking about Bitcoins, I beg to disagree, because For example, a 1 Turkish lira coin from 2009 might be more valuable to a collector than a 1 Turkish lira minted in 2022, right? Same thing applies to Bitcoin. If you had a Bitcoin that is sent to you by Satoshi in 2009, it will be more valuable, right? So saying that this all of the Bitcoins are equal is not correct, because you can do some stuff with the date they are minted. Similarly, as I mentioned, older Bitcoins might be preferable for some. For example, consider a Bitcoin conference where early adopters receive 20% fee reduction when they pay with Bitcoins that were mined before 2011, for example. So you can play any games, you can even color Bitcoins and, give rewards and so on and so forth. So the date they are minted might be an interesting area to work on. Yes. So let's talk about pay to public key hash, because we have wallets, so we have some addresses. So let's look at how they are created and how we can make transaction to these addresses. So let K, a point on this elliptic curve, be a public key. Okay. So recall that we randomly choose a private key and add the base point itself that many times, and then obtain this point K. Okay. This will be used as a public key. So it's 256 bit X and Y coordinates, result in 512-bit value. So you put them into SHA-256, then RIPE-MD 160, and the result A is the resulting Bitcoin address. So you're putting it into two hash functions, but the last one is RIPE-MD, so the output is 160 bits, in other words, 20 bytes. Okay. So this is actually the address you are sending. But if you write this down, most probably you will make a mistake when you give it to some other people. So we have some other measures to turn it into a valid address. So A is 20 bytes. Now we are going to encode it with base 58, right? Because otherwise, if you write it in hexadecimals, it will be, there might be some mistakes. Moreover, if you try to write it as ASCII characters, since these are random values, not every ASCII character is printable, right? You cannot write it down on the piece of paper. So you cannot turn it into 20 characters. That is what I'm saying. This is why we need some encoding. Of course, base 64 is used a lot of times in computer science, but in Bitcoin, we actually remove 6 characters. So this is why we use something called base 56. So we use that as follows. Our data is this A. So we add a prefix to data called the version byte. Then compute the double SHA-256 of this prefix and your data. Okay. The first 4 bytes of the double hash called checksum is appended to our prefix and data. So the result is now your RIPE-MD output, prefix, which is the version byte, then this checksum, which is double SHA-256 output, but you don't write the whole 256 bits. You simply write 4 bytes, which is 32 bits, and you use as a checksum, so that if you make a mistake when you type an address, the checksum will, warn you. Otherwise, you can send money to an address that belongs to no one, and in that scenario, that money is lost. Okay. So we use, after this, append, when we add these values, not add, but write it next to each other, then we convert them into base 58 alphabet. So base 58 alphabet is like this. As you can see, it contains almost every character in English alphabet and some numbers. But most importantly, you can see that there is no 0 here, because you can mistake it with capital O or small o, right? So for this reason, capital O is also removed. As you can see, small l is not here, because sometimes it is mistaken by 1. So these are chosen according to, so that humans cannot make big errors. So assume that our A, which was, RIPE-MD output, was something like this. So of course, it is very hard to find an input that gives this output, because I chose it in this, special format. But assume that this is our RIPE-MD output, right? Then we add the version, which is 00 here in hexadecimal. So this is our new value B, whole thing. Then we put B to double SHA-256, obtain the output like this. Well, I already said that we don't use all of them as a checksum, but only the 32 bits or 4 bytes, which is this. Okay. So you take this checksum, concatenate it to B, which is this. Then make the conversion from hexadecimal to base 58 alphabet. So for this reason, as you can see, the first byte comes from the version, which is 0, right? So 0 is mapped to 1 in base 58. This is why all of the Bitcoin addresses starts with 1. All of the initial Bitcoins, let's say, because with the updates, we will see that some addresses starts with 3 because they will be script addresses. And with the new updates, we will see BC1 addresses, okay? But traditional addresses starts with 1. So this is how they're calculated. So this looks like a valid Bitcoin address. So if you try to send money to this address, none of the wallets software will warn you because the checksum will be valid for this input, okay? But of course, this is the address you write, but actually you are sending money to A, which was the, 20 byte of RIPE-MD output, okay? So you can write a software to perform this, encoding and decoding, but there are also some web pages where you can write, input and calculate the SHA-256 or base 58. So here are some examples I found on the internet, so you can just use them if you want to see how this base 58 address is obtained and so on, okay? So as you can see, the base 58 conversion actually turns this address something look like random. So, but there are some addresses where it starts with English words. So question is, how can that be, right? We call them vanity addresses. Vanity addresses are Bitcoin addresses that contain human readable messages. So here's an example from this famous blog. As you can see, this money, as you can see now, the address starts with BC1. So this is an address created with the latest address updates. So it is not an old address. But the money is sent to addresses that start with 1, traditional addresses. But as you can see, here the word God can be seen and Bible here can be seen. So it is actually reference to the number 666, which appears in the Bible as the number of the beast, right? So question is, how can somebody create such an address, right? Because you don't have control here, because you randomly create a public key, then convert it into this address, right? So the answer is not that hard. Vanity addresses require generating and testing billions of candidate private keys until a Bitcoin address with the desired pattern is found. So you randomly choose your private key, calculate the public key, calculate the base 58 encoding, and look if it starts with the word you wanted. If it does, then go and choose another random private key and repeat this process again and again. And this is how things happen. For instance, here is a block number where I think it was about from WikiLeaks, because there was a news about somebody was jailed. So here they sent the message, we are fine, 8chan post fake, right? You can send a message to other people like this. So how many trials I need to perform if I want a vanity address? So if I want my vanity address with a specific character, since with the 58 encoding, there are actually 58 characters, which is 2 to the 5. So you need this many trials, right? In other words, 58. But if you want 2 characters to be specified by you, you need to perform this many operations. This is more than 2,000. So the character, the word God requires 3 characters. Again, you need to perform this many, try this many private keys to see if it starts with God. But again, this number is not that huge. But as you can see, after some point on, the numbers are really increasing, right? I mean, with your personal computer, trying this many is not that hard. But after some point on, these numbers will not be reachable even with multiple GPUs you have. Okay, so you can choose first some characters as vanity addresses if you have the computational power. That is the catch here. Yes, base 58 encoding, I told you that the public keys start with the 0, which turn into 1 when you convert it into base 58. So there are some other versions, like in hexadecimal 05, which turns into 3. And these addresses are used for pay-to-script hash addresses. So most probably you have seen Bitcoin addresses that starts with 3. Also for private keys, you can start with 80, but this results in different characters depending on the next character that comes after this byte. So private keys, when converted into base 58, starts with 5K R or L. This is important for forensics people. So at a crime scene, if you observe random numbers starting with these characters, most probably it is a private key. Also on a computer, when you try to search, you should start to search this kind of stuff and to obtain private keys. So private keys are in this format if they are not encrypted. That is the idea. The 4 bytes of double SHA-256 checksum is used to detect errors. So question is, does it detect every error, right? So question is, can I still send money to an address which actually checksum is not correct? So if in other words, if I press a wrong button, will it still be a valid address? That is the question. So error detection prevents sending Bitcoins to invalid addresses, right? If an error occurs on the base 58 representation, here I'm meaning not the checksum, but the previous parts. So you click the wrong key on your computer. So if an error occurs, when the error corresponds to the checksum, we always detect the error, right? Because we will calculate the checksum and they will not match. Right? That is the obvious thing. But if the error occurs in the public key hash, you have a different input to double SHA-256. So the whole output will be different. But recall that we are not looking at the whole 256 bit SHA-2 output. We are only looking at the first 4 bytes, which is 32 bit. So 2 different inputs might give you the same 4-byte beginning SHA-256. So question is, what is the chances of this happening? The chances of this happening is 1/2 to the 32. So you detect error with 1 minus this probability, which is 0.999, and as you see, it is a very low probability event. So if you're that unlucky, then maybe you should buy a lottery ticket afterwards. So we detect errors most of the time. That is the catch. So traditional Bitcoin addresses begin with the number 1. Anyone can send Bitcoin to a 1 address, but that Bitcoin can only be spent by representing the corresponding private key signature and public key hash. Okay, we will talk more about them when we talk about transactions. So Bitcoin addresses that begin with 3 are pay-to-script hash addresses. So here, the address is obtained as a hash of some script. Okay, but sometimes erroneously called multi-signature or multi-sig addresses, because you can write in your script that it is a multi-signature, but you can also write something else, right? So not every 3 address is a multi-signature. That is what I'm trying to tell. As an example, I will show in the transactions where a script is written so that money can be claimed only when you provide the SHA-1 collision. Same thing also applies for SHA-2 and RIPE-ND. So there are some scripts where some money is there. You can claim it if you can find a collision for RIPE-ND 160 or SHA-256. But of course, currently it doesn't going to happen quite time soon, right? So we are talking about 3 addresses. They designate the beneficiary of a Bitcoin transaction as the hash of a script instead of the owner of the public key. So whenever you want to claim this, you have to provide the script. So you have to store those scripts. So this feature actually was introduced in January 2012 with BIP 16. Unlike pay-to-public key hash, funds sent to 3 addresses require something more than the representation of one public key hash and one private key signature as proof of ownership. In other words, the requirements are designated at the time the address is created within the script, and all inputs to this address will be encumbered with the same requirements. So this means that you have to provide the script and everything that would return true for the script when you try to withdraw this money. So this means that whenever you do this, you have to store the script itself. So losing the script, losing the input data that you require might also end up with losing the money, right? But more importantly, here there is no checksum, because you are creating the address saying that it is hash of a script and you didn't provide the script initially. So the nodes does not know what the script is. So they don't know if the hash is correct. So if you write a wrong address that starts with 3, you actually lose that money. Okay. And it happened a lot in the past. So a pay-to-script hash address is created from a transaction script which defines who can spend the transaction output. Encoding a pay-to-script hash address involves using the same double hash function as used during creation of Bitcoin address, only applied on the script instead of the public key, as you can see here. This is the script hash. The resulting script hash is encoded with base 58 with a version prefix of in hexadecimal 5, which results in an encoded address starting with 3. As you can see, we didn't add any checksum here, so this is why you can lose money here. Finally, we have BECH32 addresses. So BECH32 is a segment address format specified by BIP0173 and is more efficient with block space. A BECH32 address is created from a public key as follows. You have a compressed public key. So this means that when we say about Bitcoin points and elliptic curve points and say it is compressed, this means that we are only looking on one coordinate, like the x coordinates. Okay. So it is an hexadecimal value 2 or 3, which shows you how it is compressed actually. Then 32 byte of the x coordinate. You write it something like this. You perform SHA-256 hashing on this public key. You obtain the output like this. Then perform RIPE-MD 160 hash. Again, you obtain this. The result of step 3 is an array of 8-bit unsigned integers, and BECH32 encoding converts this to an array of 5-bit unsigned integers. So we squash the bytes to get in hexadecimal this. In numbers, it turns into this. As 5-bit binary, it turns into this. And we add the witness version byte in front of the step 4 results. Current version is 0, so it turns into this. Then compute the checksum by using the data from step 5 and the human readable part, like this. By human readable part, we mean the BC1 input in front of it. So append the checksum to the result of step 5. We now have an array of 5-bit integers like this. So this is the checksum, by the way. Map each value to its corresponding character in BECH32 characters. So as you can see, the alphabet is now smaller. We have 32 characters. So it is harder to make mistakes here. But the mapping is defined in the encoding. Here are some examples. 0, 0 is mapped to Q, 0E is mapped to W, and so on. So this is mapped to this whole thing mapped to this. A BECH32 encoding address consists of 3 parts: human readable part, BC1, separator, this, and data at the end. Okay. This whole thing starting with BC1. The address starts with BC1. The address starts with BC1 and are typically 42 characters long, rather than 34 characters of the traditional Bitcoin addresses that start with 1. Okay. So this is because you are losing a smaller alphabet here, so that the size increases. That's one of the reasons. But again, this is With this, transaction sizes are somewhat reduced with this one, so you pay less fees if you are using this kind of addresses. So your wallet should support this in order for you to use such an address. So if your wallet software is old, you can only create traditional addresses that start with 1. In order to create addresses that start with 3, your wallet software should allow to write scripts and calculate the hash of it. And with the BC one, it should have the the update that we mentioned earlier.